Now, we are going to look at types of organic reactions. After we have discussed hydrocarbons, we have discussed alkanes, alkenes, and alkynes. Now, the mechanisms of reactions that have been followed in this case have been specific, given the type of compound we are dealing with. So, at this level, I hope that when we start discussing the types of reactions, you are able to understand what we are talking about and follow. Are we together at that level? We are saying that organic reactions are initiated by either electrophiles or nucleophiles or free radicals. So it means before you write any reaction or before you write any mechanism, you must identify those three on the compound. Either a nucleophile or an electrophile or a free radical. And when defining them, we are saying that a nucleophile is an electron-rich species. Electron-rich species might have a double bond. A double bond is an electron-rich species, right? They might also have what we call lone pairs. Lone pairs of electrons, or it might have just a charge, a negative charge. Because a negative charge is a representation of an extra electron. So a nucleophile might be of any form. Maybe it is Y with lone pairs, or it is a double bond, or it is an extra charge. Sometimes even a triple bond also works, like for example for alkynes that we have been discussing. Are we together at that point? So, a nucleophile is simply an electron-rich species. And in most cases, they are the ones that spark off the reaction. Because the nucleophile in most cases will always be looking for an electrophile. And what's an electrophile? An electrophile is simply an electron-deficient species. An electron-deficient species. Are we together? An electron-deficient species can be maybe a hydrogen atom, hydrogen ion, in most cases, is an electron-rich species. Or any compound which has an atom that is positively charged. It can also be what we call Lewis acids. Lewis acids are compounds which are also electron deficient. Some of those acids, for example, aluminium chloride, it is considered a Lewis acid. If you look at iron chloride, it is also considered as a Lewis acid. These are some of the electrophiles that we are going to be dealing with in organic chemistry. Are we together with that? So in most cases, the arrows that we use in the mechanism are always coming from the nucleophile attacking the electrophile. So the arrow should always come from the Nu going to the E, or you can call it En. So the arrow always comes from the nucleophile attacking the electrophile. The moment you write the mechanism and you realize that your arrow is coming from the electrophile attacking the nucleophile, you always know that this is wrong. Because the electrophile does not have the electrons to spark off the what? Of the reaction. In O level, we used to say a nucleophile is a donor, the electrophile is the acceptor in that level. Are we together? But in this level, we are saying a nucleophile is an electron-rich species, an electrophile is an electron-deficient species. On the other hand, a free radical is none of the above. A free radical for it just has a single or an unpaired electron. And in most cases, we denote it with a dot. So it is in form of X dot. And the free radical mechanism follows the fact that a single electron will always move in the form of a what? In form of a half arrow. We have seen those mechanisms. Are we together? It uses half hour. So every time you are dealing with organic compounds, if there is a radical, you see a dot, when you are going to form a bond, you have to use what we call half arrows. You have to use what we call half arrows. So these are the species that we are going to be dealing with in all the mechanisms of the reaction we are going to be dealing with. I've already told you the reason why we delay to teach types of organic reactions until this point is such that a student might have prior knowledge about what you are dealing with. Because you have already dealt with an nucleophile, you have already dealt with an electrophile, and a free radical. At this level, it should make sense for you. Are we together? Now, we want to look at the different reactions that are undergone by these organic compounds. The first one we are calling it substitution reaction. The first one we are calling it substitution reaction. Like the word sounds, substitution. You remove, then you replace. You remove, you replace. So that's what we're saying, that these are reactions which involve direct displacement of an atom or group of atoms by another atom or group. We just pull one group or an atom, we replace it with another. And we're saying generally, they are in this format. You are just getting this one, you are replacing it with Z. So where there was one, you get a Z there. Where there was a Z, it has been replaced by one. And a clear example we can have, for example, we can have CH2, then CH2Cl. Are we together? Now in this case, we are going to add hydroxide. So what happens is this hydroxide, maybe it is coming from sodium hydroxide, it is going to displace the chloride. It is going to displace the chloride, leading to the formation of, it's going to be CH3, CH2, then OH. So the OH has replaced the Cl. The OH has replaced the Cl. Then the Cl has been lost. And these reactions are so common, especially in alcohols and in alkyl halides. At this level, you must know that alkyl halides sit in the alkyl group with a halide. The halide can be Cl, it can be Br. And then an alcohol is the alkyl group with an OH and OH group. And we said even these substitution reactions are classified into two. They are classified into two. The first one we are calling it nucleophilic substitution reaction. The second one is called electrophilic substitution reaction. Are you following? Now we're going to first look at the nucleophilic substitution reaction. Nucleophilic substitution. We are saying these are reactions in which the electron-rich species displaces an atom or a group of atoms. And these ones are so common in what we call alkyl halides. The alkyl halides are the ones that undergo nucleophilic substitution reactions. And these ones are further divided into two. They are further divided into two. The first one we are calling it nucleophilic substitution unimolecule. Nucleophilic substitution unimolecule. In this case, the number of species in the activated complex in what we call the rate determining step is 1. Somebody will ask me, what is the rate determining step? If you remember clearly, if a reaction is going to take place, if a reaction is going to take place, if a reaction is going to take place, we have what we call reaction path. We have what we call a reaction path against energy. It it might be potential energy. We expect the reactants to be at maybe this energy level, and then the products to be at this energy level. Products, right? So we need to supply energy to the reactants for them to react. Because for a reaction to take place, we need to break bonds, to break all the bonds, right? And make what? New bonds. And make new bonds. So the breakage of all the bonds and the formation of new bonds requires energy, right? Therefore, it means that these reactants have to be provided with energy, right? And then the energy will rise up to what we call the activated complex. An activated complex is a compound which has partially broken all the bonds and partially made new bonds. Are we together? Partially broken all the bonds and partially made new bonds. So in this case, this is where the activated complex will always be, because after the activated complex has been formed, it shall go back to products. So this is what we call the activated and the activated complex. This is what we call the activated complex. A good example I can have, if for example we have AB, it is going to react with CD. It is going to react with CD. We expect in this reaction, A to form a bond with D, right? Then B to form a bond with C. Are we together? So it means I'm going to have A, B. This bond is trying to be broken, but we are still trying to form a bond with the D. So in this case, this one becomes an activated complex, whereby we are trying to break the bond AB, but we are trying to establish a bond AD. We are also trying to establish a bond between C and B. So we are trying to break this bond, but we are trying to form new bonds. So what does that mean? It means that this compound which has partially broken bonds and partially formed bonds is what we call the activated complex. Is what we call the activated complex. Now we are saying here, if we come back here, we are saying that in a nucleophilic substitution reaction, the number of species in the activated complex, the number of species in the activated complex is 1. These are reactions that are undergone by tertiary alkyl halides. Are we together? For example, an example I'm going to give, if you have CH3, C, then this is still CH3, this is also still CH3, then Cl, right? It is going to react with the OH, maybe from sodium hydroxide. What do we expect before? We expect this chloride to be replaced by the incoming OH. Remember, OH is a nucleophile. It is an electron-rich species. So a nucleophile wants to displace an atom, right? So it's going to form CH3, CH3 up, CH3 down, then OH, then plus a CH. But if you want to see the activated complex, now you have to follow the mechanism. You have to follow what? The mechanism. Let me show you the mechanism here. So in our mechanism, this reaction in this compound, for the chloride to be displaced by the OH, we have to first make sure we form what we call a carbocation. Why? Because the compound is crowded. Steric hindrance. Remember steric hindrance? So this OH is only going to come in after the chloride has first broken off. So this activated complex, in this case, will only have it will not have partially formed bonds. Because before you form a new bond, you have to first break the old one because of steric elements. So what we are going to have is the CH3, C, then CH3 here, then CH3 here, then Cl, CH3 here, Cl. So the Cl bond, the carbon chloride bond, will first break off. So this one here is going to be our activated complex. Are we together? Because we are trying to break the chloride bond. Are we together? Leading to the formation of CH3, then C, then CH3. Now this one is going to be positively charged. Then here we have CH3. So our activated complex in this case, we can also refer to it as, we can use this as a dotted bond to show that we are trying to break the carbon chloride bond. Are we together? So this activated complex here, it has only one species that is being broken. Are we together? It's just this species that is being broken, leading to the formation of a carbocation. So the OH that wants to displace this OH in this case is going to come to attack this compound. In that case, we're going to have OH. There's a negative here, but it has one pair. So this OH is attacking that carbon, right? Leading to the formation of that is CH3, then C, then even up CH3, then even down CH3, then OH. However, we can also represent it in this format. We just establish a new bond here with the OH, and this one is positive. This one is also an activated complex because it is also having partially new formed bonds. The bond is not formed completely, but it is trying to be formed. So it means in this case, we have two activated complexes. We have one where we're trying to break the bonds. Then we have one where we're trying to make new bonds. But each activated complex has one special, has one compound. That's what we call nucleophilic substitution unimolecular. It is represented as SN1. Are we together? So a clear example of a nucleophilic substitution reaction is this, whereby the tertiary alkyl halide is trying to react with a hydroxide, leading to the formation of an alcohol. So if you want the mechanism, the clear mechanism now, let us write the clear mechanism, because this one I was trying to show you the activated complexes. So the mechanism in that case, we are having CH3. These are three of them. Then C, then Cl. So this one is breaking off, and this one is the slow step. This one is the slow step. Why do we say it is the slow step? Because we are trying to break this old bond. Remember, it was stable. So we are trying to break it, so we have to put in a lot of energy to break the bond, right? That will form CH3, then C, these are three of them, then three bonds. We are forming a carbocation. So in a substitution nucleophilic reaction, whereby we have whereby we are having a unimolecular reaction, this will lead to the formation of what we call a carbocation. Then the OH in this case is going to come directly and will do what? It will attack, leading to the formation of CH3, then 3, then COH. However, if it was bimolecular, because we have unimolecular, then we have bimolecular. If it is bimolecular, we are going to see as this bond is being broken off, another one is being formed simultaneously. So it means in this case, the OH will not have to wait for the chloride to first break off. The OH will attach immediately, then the chloride will break off. In that case, the activated complex will have two species. Will have two species, as you are going to see here. We are saying that the nucleophilic substitution reaction, which is bimolecular, SN2, the number of species involved in the activated complex in the redetermining step is 2. And a clear example here is if I use primary alkyl halide. For example, if I'm using CH3, CH2, Cl, it is reacting still with OH, right? How we expect the chloride to be replaced so that we form CH3, CH2, OH, then plus the Cl. But this one follows the fact that the activated complex will have two species. Let me show you what I'm talking about. That if in this case, if you are going to look at the mechanism, you are having CH3, CH2, then Cl. The OH attacks first. Remember, OH is our nucleophile. It has lone pairs, so the lone pairs will come to attack the chloride, I mean the carbon with the functional group, then the chloride will break off. The chloride will break off. Do you see that? Leading to the formation of course you're going to say, this is our rate determining step, where we are letting go of the chloride, and the OH is coming in, leading to the formation of CH3, CH2, OH. But you see, we are trying to form a new bond and breaking the old one simultaneously at the same time. So how the activated complex look like? The activated complex would look like, so we are having CH3, CH2. So we are trying to break this C, or the bond, right? But we are trying to establish a new bond with what? With OH. We are trying to establish a new bond with OH. So this one is going to be our activated complex in this case. One, because the OH comes in simultaneously as the chloride is breaking off. So how many species do we have here? We have the OH, and then we have the alkyl chloride. Two species. So in this case, there are two species that are involved in the rate determining step. I hope you understand that. So, the nucleophilic substitution reactions that are bimolecular are typical for primary alkyl halides. And sometimes in some reactions, secondary alkyl halides can go through the bimolecular reactions. But because even the secondary alkyl halide is also slightly what? Slightly bumpy, slightly crowded, then we are going to see that also sometimes it undergoes unimolecular leading to the formation of carbon